later on I will post it on the campus. I think we can start. Anyway, so this course is focusing with the how do description languages. How do we description language? Okay. The lecture for today is a multiple parts. First, it's actually telling you how can you access the materials through the cameras, what is exactly you're expecting from this course, how the grades will be distributed. I will ask you to build a group, so because there is a project associated with this course, and then we'll have like refreshing your knowledge about 2300 from combinational circuit to sequential circuit, whatever it's going to be, like 2 lectures, and then we can move really deeply inside the language and syntax and how can we translate the digital logic we learned 2300 into code that will be deployed on the FPGA chip. Okay, so I'll share my screen. Everybody can see my screen?
Yeah.
Yeah.
So now we are in Canvas. You guys are aware with Canvas, right? Have you used it before, right?
Yes.
Yeah, we used it before, Professor.
Yes. Okay. So we are now on the course. And in this course, you will find what there is announcement, there is assignment, discussions, grade, whatever, right? So the syllabus, I already posted there. Okay. And in announcements, I would recommend you guys from time to time, every week I will be sending like a fixed announcement. So this week I already sent you information. Have you received it?
Yeah.
Yeah. Okay. I just want to be sure that everybody know what's going on. Okay. So we're gonna go in the syllabus, and from the syllabus I'll continue story. Okay. Why we are taking this course besides graduating? Yeah. We are taking this course so we will understand the differences between combinational circuits, sequential circuit that can be mapped on a reconfigurable computing platform as FPGA. What does it mean, reconfigurable? It means the chip can be changed based on the streaming that I will load it on it. Normally, we have dealt with the old school chip, which is like a chip that you program, you write a software for it, but the architecture on the chip is fixed. An example for it is the microcontroller, and you guys already had microcontroller on 3301, right? But if I would like to change, the little bit architecture inside that microcontroller, I cannot, unless the microcontroller is mapped on the reconfigurable platform as FPGA. FPGA stands for Field Programmable Gate Array. So FPGA is a field programmable gate array. It's an array, has a ton of switches that we can change it from 1 to 0 or 0 to 1. It depends on what is the final product I would like to have on the chip. So as a student, I will learn out of this to understand how can I program combinational circuit on FPGA? How can I describe finite state machine on FPGA? How can I build flip-flops in FPGA? And also, how can I take the timing in the consideration while I'm building a circuit so that will not affect on the maximum frequency that's used for feeding the sequential circuit. Also, we're gonna learn differences between the data path and the control passes that will be mapped on the chip. And on top of that, we'll be able to build circuits, like sequential circuit, like, sequential multiplier, sequential divider, traffic controllers, vending machine controllers, and whatever else that, myself and you guys will decide. To be qualified to take in this course, you need to pass the 2300 and 2300 lab. And I believe all of you already passed 2300 and 2300 lab, right? Also, this course coming in two pieces. So you have the course, which is 3300, and you have the lab, which is 3300 lab. I believe not everybody in my course is taking the lab with me, right? Normally, it's better to have both with the same instructor. That's normally, but if your time, conflict and so on is not allowing you, there is no problem. How are we gonna actually manage this course? So this course up to February 12th will be virtual. So we're gonna be based on Zoom. And when we return it back to in person, hopefully by February 12th, they're gonna be hosted on Building 9 and Lab 507 in the 5th floor. And our lectures will be dedicated on Monday, 2:30 to 5:15 p.m. And to make it more easy for everybody, I decided to build a Slack channel, which is called ECE3300 Spring 2022. It should be not 2021. This is a type of affix. Okay. Now, what is this Slack? So Slack is like Discord. You guys use Discord, right? Slack, it's a program, it's a professional program used by the top companies like Intel, IBM, Xilinx, Microsoft, and LinkedIn, and Visa, and Visa card, MasterCard, all these guys. Okay. Basically, if you look here, I already opened the Slack. Everybody can see Slack, right?
Yeah.
So if I click here, I already have a multiple groups. Rico IoT, I dedicated for Calpoli activities. QSkin is for my collaborator and research for quantum with IBM. So if you go here, Rico IoT, you click here. Next time, I don't know, the internet's very slow. Wow, that's very slow, too slow. I think because of the power outage, right? You guys are aware of it, right? Hello, can you guys hear me?
Yeah, we can hear you, Professor.
Yeah, just to be sure that you guys hear me because I know the internet is crazy. Let's hope that it will open. You can set it up as an app, but I just open it on the browser, right? I don't know why it's taking forever. Let's hope it will open. Okay, open. Yes. Anyway, so you will find a list of the channels I already have created for Calpoli activities, right? So here's senior projects, summer, fall, spring, whatever. And even also, here's Intel process with my team from Calpoli. Here's lightweight crypto with Oregon National Lab with Calpoli. And here's NASA teams with Calpoli. Anything with Calpoli you'll find it here. Okay. So we are here. Spring 2022, right? Here. So I would recommend every single member who I already invited him through the email. So you check the university email address, you'll find that there is an invitation sent to you about joining Slack, right? To add his GitHub username in the channel. I know some of you guys already send it to me individually, but it's really hard for me to go like one by one. Better for me to collect it from the Slack channel. Okay? It would be great if you guys posted there. Sounds good? Okay, now we're gonna go back to here, okay? For the Zoom activities or virtual activities, we're gonna be using the link that you guys already accessed and the password in front of you 113 whatever 118. In front of you, I'm a Professor Muhammad El-Hadedy, and I'm actually assistant professor at California State Polytechnic University in ECE department, and also a scientist for University of Illinois Urbana-Champaign and University of Louisiana Lafayette. And I work beside that with the US Air Force, Navy, and NASA. Office hours this semester is Monday, Wednesday, 5:30 to 7:30, and my office number is 2594, and my email address, if you guys still remember, 2300 is mainly finance machine, so mainly at cpp.edu. To access my office hours, what you need to do is actually to click on the calendly.com that I associated for the Cal Poly activities. You will reserve a time slot, and every single time slot you have is basically 15 minutes. So you have a window of 15 minutes. You can address all of your concerns or questions, and I will be with you online so we can discuss it. Okay. Beside Slack channel, so when you go in the Slack channel here, you can start writing questions. So every participant of the course can see the questions, and I will do my best from time to time to answer back and forth. This is beside the office hours. Okay. Now, what type of textbook we're gonna use during this semester? To be honest, you don't need. But if you want, there is the Charles Roth digital system design using Verilog, and this is like the main one I use. But you can. There is a bunch of materials in internet you can use. There is infinite number of materials in internet. Stephen Brown, Fundamental of Digital Logic Design, and of course, my colleague, Dr. Rafiq Zaman from the ECE department here for digital logic and microcontrollers. And this is actually going through the definitions of the combinational sequential circuit up to the introduction of the Verilog as a hardware description language. How can we evaluate you as a student participating in this course so you can get a grade? So this course activity will be broken into parts. The first part is a quiz, number 1, and that's basically 5% of the total grade. And the date is already set it up for March 2nd, which is in the week number 6. Then midterm number 1 is 20%, and they're gonna be the date of March 14th, which is week number 8. Then quiz number 2 is a 5%, and that will be in April 4th and the week 11th. Midterm number 2, 20%, and that will be in April 18th. And in the top of that, there is a project you guys will be working on, and they're gonna be the due for it is the March 3rd. So let's talk about the project. So before I started this course, I was actually in the lecture for 4300. And I asked the students, the members of this course, one of you guys to create a Google document, and you share it with me and the rest of the students participate. What I want you to do is the following. So number of total students we have in this course is 32 students. We have 32 students. Okay, so So I want you guys to break the course to 16 teams. So you're gonna make group A, group B, group C, group D. The one who will make the Google document now, right? And then, I mean, my honest advice, you select the partner. And you guys will write group A, and then you put your name and your partner name, and in front of your name, you're gonna make a parentheses and you put your GitHub username. So I will show you, for instance, here the people in the 40300 they did that. So group A, they put his name and then his GitHub ID, username, his name, GitHub username, and so on and so on. So you're gonna do this. So normally, I will tell you traditional. I used to go ahead and I choose the people randomly. But I noticed some people were not like that. Okay? Because maybe not feeling great, maybe they don't know the person, it's really hard. So I would say that I will leave it for you guys. And you have a 1 week from now. That means the coming Monday, you're gonna be the due. That means you guys will be done. And based on that, I will create a GitHub groups. And I will use the GitHub username you already have, so I can add you there. Why we need this group? So you will load your codes for the project and the document associated there in that GitHub group. Have you guys ever used GitHub?
I haven't, no. Personally, no.
Okay, it's really straightforward. So after we finish today's lecture, I will go in announcement and I will send you, I will put you a link of video, how can you create a GitHub username. Okay. You just need to use it like Dropbox. You just put the subject. Something to tell you. I believe all of you guys also seeking internship in summer, right? 99% of the companies after the pandemic and even before the pandemic prefer people to work online. And most likely people start using GitHub and something similar to GitHub to share codes. So, the group participants, you can still work together in the same code. Okay? Sounds good? So,
yes.
One of you guys already sent the link, right? Anybody created the link? One of you guys, can you please
For a Google Doc?
Google Doc, yes.
All right, I'll go ahead and do it.
Call it for ECE3300 SP2022. Then you guys will do it, as I said, group A, then 2 people together, every name in front of him is GitHub username. Sounds good? Okay, back to the syllabus. Now, we don't know what will happen with the pandemic, right? So imagine, just imagine, that's in theory. Hopefully it will not happen. Imagine that, unfortunately, we're gonna stuck with one online for 1 more semester, right? So for exams, I will post the exam on the grid scope. You guys will have from 8 a.m. to midnight to answer the questions, but of course, individually. Everybody has his own exam, right? And you posted the question there, and you posted the answer there. No, you're fine then. You're fine. I'm recording, so you can watch it again, okay? So anyway, so in case of emergency, we're gonna use Gradescope. I will post there the questions, and then you will get it answered. You load it there. Then I grade it, and then you guys will get your grades and so on, right? Also, if we're turning back to normal life by February 12th, exams will be on school, like during the course time, like 2:30 to 5:15. So you can have the exam, you can do your work and you'll be done. Okay? Of course, when I said, schedule and office hours subject to change without notice, because who knows what will happen with the pandemic. So, yeah. Anyway, now great. To be sure that you get an A, your grade it has to be between 94 to 100%. And then you check the rest based on the whatever listed in front of you. But if you unfortunately get 60 or less, that will be F. Higher, that will be going in D minus and up. We are kind of like, needing this course because, this course is 99% of companies around here hiring with Verilog, VHDL, and System Verilog. And those three I mentioned now, they call them hardware description languages. Okay.
What are they called? Can you say it one more time?
Hardware, I'm gonna write down on the tablet. Hardware description languages. They are kind of software, but they're not software. Okay, I will give you now a very fancy map on the tablet. Anyway, what topics this course is covering? Frankly speaking, 2300, but on the chip. So whatever within the 2300 is on the chip. And building more complex and complicated systems. Okay, but topics, those. So we will look into Verilog modeling. How can we start writing code on the Verilog? There is a strategy we can use. So strategy, they call it modeling. So it can be structural modeling or data flow modeling and behavior modeling. Structure modeling, kind of the other people call it when they start using gate, they call it gate level modeling. Gate level modeling. Thank you, Gerard, for the link. So you guys can see the link that already Gerard sent. So you guys go ahead and you start filling in front of the group your name and the parentheses, your username for it. Okay. Anyway, so structure, that means I start building counters, for instance, with flip-flops. I start building ALU, arithmetic, logic, and so on. Behavior is like describing the relation between input and output. Everything will be going now in details in a moment. And data flow is basically building the data passes and moving the data from block to the others using the pipelining strategy or single cycle implementation and so on. Also, we're gonna be able to work on the combinational circuit, and we're describing it using one of the modeling. It can be described by the structure, data flow, or behavior. We're gonna learn about timing. So I want you guys to focus very, very, very well with the lectures that I will be spending time on it for the timing, because 99% of questions for the people who join industry is based on time. One of the really, really nice institutes you can join for government is called national labs, right? Like Sandia Lab, Los Alamos National Labs, Brookhaven National Lab, Livermore Lawrence National Lab, Berkeley Lab, SLAC, all of those guys. So all of these labs actually were interested and in favor, and people work with timing on the how to do description languages on chip. So when we say timing, that means we can look into when the circuit will not be stable, when the circuit will be a kind of a stable, metastable, when the circuit will be performing, when the circuit will be in idle, setup time, hold time, when the circuit can be using asynchronous input versus synchronized input, and how can you calculate maximum frequency based on the timing of the circuit, and what is the effect of having wires a lot between of the input and output in a skew. Then this course also will be covering the sequential circuit elements, like how do you build finite state machine based on whether they're going to be mainly finite state machine, more finite state machine. How can you build counters, up counters, down counters, rebel counters, random counters, specific customized counters. Also, how can you build type of registers? Going to be parallel input, parallel output, serial input, serial output, based on the configuration. And also you'll be able to build flip-flops and start using them together in a system with counters and registers. We're gonna have a lecture about, what is the elements inside FPGA? What is exactly we are programming inside FPGA? How those guys are connected based on the software we are using. Also, we're gonna be learning more about how can we map code on the FPGA, and how can we write RTL that will be synthesized and mapped on the chip. We're gonna learn also about can we represent data paths and control paths, which is called a data path unit and control unit. We're gonna learn a flavor of verification. How can we verify our code is actually doing the specification or not? And we can start building like more complicated elements like multipliers, washing machine controller, vending machines, traffic light controller, and CPUs and so on. I'm gonna go now in details in this, but at least we need to cover the syllabus. Policies. When I say no negotiation for grading, it doesn't mean that you have rights to discuss. We are humans, and I'm a human, so that means I'm also exposing. Maybe I can make mistake, right? I'm human, right? So if notice there is a mistake in the grade, of course you are allowed to discuss with me, and I'm more than happy to help. But other negotiation, like you understand, I used to be a student, you guys are student, and the ways of negotiation. But anyway, like negotiation about partial credits, I do the best to give you the best of the partial credits. Okay. Also, I would say work for yourself by yourself, which is mean avoid cheating, because when you will be hired, yeah, maybe you can pass and you can get A, but when you are hired, the responsibility will be assigned to you. It will be to you, not to the neighbors. So just do your best, because this is very important. Unfortunately, I will be reporting if I see any cheating. And of course, I don't like that because I don't want anybody to get hurt, but please do your best to work and learn as much as you can by yourself. And of course, there is no problem if you can ask questions to the students and even myself on the Slack or even in the chat, whatever you want. In terms of exams, for some reason, you got sick, right? Or some family issues, concern happened, or something happened. Feel free to contact me and we can discuss, and I will do my best to help you based on the situation. So I'm here not really harsh, but I'm trying to do the best to help you to be the best engineer ever you can see in your life. And if, for instance, if something happened in a quiz time or whatever, I can push to help you for sure. Okay. Do you have any question regarding the syllabus so far? Is there any concern?
No, Professor. I think we're good.
So feel free to understand that we are like a family, okay? So every single member here, including me, we are like a family now. So as a family, we take care of each other, right? So we're gonna do the best so you guys will enjoy this course and you will do your best to learn. Okay. Now I'm gonna stop sharing this and I will start sharing my tablet so I can write stuff. Belly, I don't think that will be allowed. So better to be like 2-2. When I start adding more people, then that will make it more difficult, because I would like to be sure that the both members will do their best and both members will learn from each other. That makes sense? Thanks so much. Anyway, now I'm gonna be sharing my tab and I will start writing some stuff. Then I will start also making some revision of some sequential combination circuit, whatever, and then I will open in front of you the software and I tell you a story. But before we actually go, I want you to remember one more important thing. We need the board. And the board is used for this course is what? Nexus A7 or Nexus 4 DDR. I'm sure that not all of you have board, right? So the best for you is to buy the board. So maybe I can share again the screen and I tell you a story about the board. So for the board, they have the A7 now, right? Here's Digilin. So for academic price is 171.75. I would recommend to buy it as soon because it's currently out of stock. But you know, if you can lend it from somebody you know has taken this course, stuff like that, that will be easy, right? You agree?
Professor, I have a question.
Yes, sir.
Would you want us each to buy one or one per partner?
It's better for you to buy one per partner.
Okay, sounds good.
You will need it for other courses, by the way. I'm gonna write down what courses you will need it for, okay? But you know, we have ton of courses on the department you're gonna use. Okay, so here, I'm sure people in Amazon, you know, it's like a big prices now. Very interesting. Oh my Lord. You see that? 400 bucks. It's crazy. I don't know if I told you that I was looking for a Raspberry Pi, right? It used to be $20, $30, right? Now it's $200. That's really insane because of this supply chain shortage. Have you guys following the news? I think Intel now is like investing billions of dollars in building their fabs in Ohio and Arizona. They're building like a 3 or 4 fabs. But from where you guys gonna buy it? I think you might buy it. Let's see. Anyway, I'm sure that you will find some. You guys have your friends here, right? Oh, only the 50 is out of stock? No, I mean, this is the official Calpoli, what's called, ECE department recommended board. Nexus at least, you know, Nexus A7. I think you can find the DD4, the Nexus 4 DDR, right? The old one, people of course will be selling it and it will be cheaper at least.
How soon do we need it by?
Huh?
How soon do we need it by?
I mean, till now you can run the programs, right? But you play with the software, but you don't need it for now. Yeah, Mario, 100 T's, if you find it, buy it. You know what is the difference, right? 50 T and 100 T, let me write down. If you guys understand what's going on. Let me share my screen. Can you see my tablet?
No.
Oh,
There you go,
you need,
we can see it now.
of course, you need the board for the lab, by the way. That's why, you know, it's better for you to buy it. Now I'm gonna create easy. Everybody can see it? Okay, now here is the FPGA chip, right? Right? There are something that's called family. Okay, so it depends on who is the vendor. So the vendor for us is called what? Xilinx, right? So Xilinx have multiple families. Okay, what is this families? Spartan, Artix, Ultra, Scale, Kentex, Vertex, Versal, and Alveo. And we have more, okay? So I have a Spartan, Artix, whatever, right? So now, Artix is the lower in the family. Artix is the lower in what in the family. So we open up. Now, Artix itself, it has subfamilies. And these subfamilies based on number of resources on the chip. So 50T, 100T, or whatever else you have, 50 is the smallest. 100 has more resources, but they are identical. They are what? Identical. That makes sense? Then, don't forget, we are talking until now about what? That chip, which is called FPGA, right? Then Digilant will buy like a big pile of FPGA chip from who? Xilinx. So basically, you know, Digilant is the ally of Xilinx, like a partner, right? Those Digilant, they build a PCB board. So they put you the chip here and then start putting your switches, LEDs, a bunch of other switches, USB, you know, PMOD units here, Ethernet, VGA, and so on. So this is the chip. So the board is called what? A7, right? The Nexus. Nexus coming from Digital, the word. A7 because it's Artix 7. 50T, that means, you know, the chip have number of resources are really small or big or whatever. I'm gonna write you what is details inside, okay? Or 100T, that's another one, but it's from the family of the 7. If you even, you know, figure out to buy the Nexus 4, right? It's still doing the job, and so on. That makes sense? Does it make any sense to anybody? To everybody? Now,
Yep.
Let me tell you a story. It's a big story, okay? But I want you to focus while I'm telling you the story. It's very interesting, okay? You need to know what you're gonna do with this research, or the whole entire topic, right? First of all, we're gonna talk about why we actually studying this, right? Don't worry about this, you know, formalities of syllabus, whatever. Let's go like in detail, right? Now, in 2300, you used to get like the breadboard, right? And you get the wiring, and you get the ICs, and you start connecting between them, you build the circuit. Do you agree? Too much headache. Why? Because end of the day, that imagine that, you know, you have a ton of wires, and one of them is losing in the middle. How are you gonna fix it? You have to remove everything and put everything back, right? So FPGA helps you to overcome with this problem. And instead of doing this wiring, you're gonna do it on the chip. So all of this guy will be invented inside the chip. And we're gonna use tools for it. So this course is pieces, right? Tools, language, and programming the chip. That's good. What tools we gonna use? Verilog. What language used for programming this chip? HDL or HLS? What does HDL mean? Hardware description languages. What does HLS mean? High level synthesis. What is before the HLS was used? Another language is called OpenCL. Have you guys heard these terms before?
I've only heard of HDL before.
So anyway, I'm gonna go through everything. You know, today is like introduction, right? Now, HDL, right? There are 3 different types of languages, and each one has a story. Okay, so do 3 like this. Verilog, VHDL, system. Very traditionally, there was just VHDL and Verilog. Somebody will tell me, so what is this? That was used for what? Verification. And I will tell you what is verification, okay? So Verilog, it was the language used by civilian industry. VHDL is the language for the US Air Force. So the one who invented VHDL, US Air Force. Their baby, is it? Verilog, Intel, Xilinx, Altera, you know, IBM, whatever. Even defense contractors will be using VHDL. Now there is big difference between of them. It's just a syntax, but it's concept same. Okay. So far so good. Now, what is the story of system Verilog? So system Verilog is Verilog, but you know they made set of rules to do verification. What is verification? When you build a block, you check whether this block is doing the job or not. Sounds good? We're gonna go through this later, but you know, at least you understand. So how many languages we have? Verilog, VHDL, system Verilog. Sounds good? Now, HLS. HLS, it's a research community, man. A research community, like MIT, Intel, Harvard, UIUC, Carnegie Mellon, whatever. So there is in US, the universities are what levels. So there is something it's called R schools, and there is another one it's called T schools. Have you guys heard about that? R stand for research schools. T are teaching schools. Levels of R's: R1, R2, R3. Teaching schools, non-PhD, granting institutes, community college, right? are, it has the top schools in the nation. MIT, Harvard, Stanford, UIUC, CMU, Carnegie Mellon, and the big list of institutes, 200 institutes in the United States are one. R2, 200, 300 institutes. R3, several. Okay, like 300 institutes. We are here in calculating what in this. Okay. So who built this languages? Oh. What HLS? HLS, Intel, Xilinx. Xilinx was actually the one who needed HLS. They built their own HLS, so they call it Xilinx HLS. So what is HLS? You write something is called C or System C, and there is a compiler to convert it to Verilog, or VHDL, or System Verilog. So you write normal C, and then compiler will take care of it. It will convert it to Verilog. Then you deploy it to the chip. Sounds good? Why they do this? Because some computer scientists, they don't know anything about circuit, right? They use. There is OpenCL. OpenCL have been made by who? Intel. And they get rid of it now, and they're using HLS. Okay? OpenC also is based on what? C. Then there is community like UC Berkeley. Have you guys heard about UC Berkeley, right? UC Berkeley, they build a language based on something is called Scala. Scala. It's like a kind of Java, but it's not Java, it's kind of, okay? So Scala, they built out of something is called Chisel. You write C, something similar like HLS and OpenCL, but it's customized in a better performance. And you find this language on GitHub. Okay. There is other era of languages, industry and defense sponsoring research schools and our schools and so on to build it, which is based on Python. There is one is called Verilog. My team built Verilog. And there is one is called MyHDL. And there is many. You can write Python and convert it to Verilog, and then you deploy, you run the tools, and it will be what deploying the chip and make something of it. So far, do you understand what's going on, or is it clear so far what is the content I already presented? Or do you have any question? Or I should move forward? Hello?
Yeah, someone asked a question.
So far, so good? No,
There's a question in the comments.
Somebody said about HLS. No, unfortunately, we're going to be just focusing on Verilog. So that's why I'm taking you to Verilog now. Okay? But HLS is something, actually, I use it with my research teams in senior projects and thesis and for master and stuff. Anyway, now we're going to pick whatever we need, Verilog. So now we know that we're going to use Vivado as a tool, and in language, we're going to use what? Verilog. Right? As we're going to use Verilog, we need to know that, while we are learning Verilog, there is two different types of syntax we will be using. Some syntax will be used for building the circuit that we need to deploy on the chip. And we call the out of this RTL, register transfer logic. Register transfer logic. RTL. Those are going to be ending up to be what the resources on the chip, so we can be programming. And there's another syntax we'll be using in Verilog that will be verifying before we deploy on the chip whether this RTL is valid or not. And those will be using for what? Verification. It's called what? Verification. There is a big topic of research for verification. One of the verification methodologies used is called UVM. Other one is called OVM. If you are fresh graduate and you know UVM, your salary started in the Silicon Valley with 175K. UVM, OVM. We're not gonna go through this in our course, but you know, if you like to learn it, there is a professor in UIUC, my school, when I was there, and I'm still working for them. Those guys already built something is called UVM for non-believer or something like that on a platform for learning is called Coursera. Have you guys heard about Coursera?
Kind of.
Coursera. So that professor putting the news about, oh, who actually did that, who did that, who did this, and people learned from this and that. They took the course online and they passed it and they did the project and everything. And now they're working for Intel, working for, you know, big top companies. Okay. I know one of them is now a manager. Okay, anyway, but what verification we're gonna use? We are gonna use something that's called formal RTL verification, which is helping us to build something. You're gonna hear it from now on. It's called test bench. Test bench. From now on, you're gonna hear this. When you build your circuit, you build this bench. Sounds good? Okay. Now, the programmability. How we're gonna program. So, the programming, after you finish the RTL stack, after you finish your RTL stack, you're gonna put the code in a way that I will show it to you that will be synthesized. So, you know, we're gonna now active the tool. Synthesizing, place, and route, then generating bit history, then deploying on chip. So far so good. Who gonna help us to do this? Verilog. Who can help us to do this? Verilog. But of course, before we go and start the synthesis, we will check our code whether that is valid or not using test bench. Why? Because every time you will run this RTL inside this synthesis, it will take a huge amount of time. So for saving your time, you need to check this code is doing what you want by the test bench, then you can start the synthesis. So far so good? We're gonna go through this like in details, but I'm just giving you the big picture. Sounds good? Be sure to understand every single board, it has its own IO interface file. IO interface file. They call it XDC. So historically, traditionally, Xilinx, they have their file was called UCF, but wasn't their tool is called ISE. But now this tool is called Vivado, which is a tool had been built by Professor Jason Kong from University of Los Angeles, UCLA, University of California, Los Angeles, UCLA. he built up with his PhD students team a startup company, and they call it Vivado. Then Xilinx acquired Vivado and retired ISE. So Vivado now is the official Xilinx supported. How are you gonna deploy? How are you gonna install the software? This is also something you need to learn, right? So I don't want you to waste your time when you're actually waiting for your board or whatever. You know what will happen, right? So we need to download the software, right? So how are we gonna download the software? I'm gonna start now sharing my PC screen so I can show you what you're gonna do. Now, we don't need Digilent. Digilent, you guys will take care of it. Some of you said 100 T's exist. Buy it. You will never lose it. And later on, I will tell you how many courses you will need. But you know, now I'm gonna go to Google. I don't know anything about this subject of event. So I start with you like that, right? So I'm gonna write here, you know, download Vivado. Okay. I found the first link say download Vivado. Xilinx, right? Everybody can see it, right? Now, Vivado is bunch of generation. Vivado, bunch of generation. So, since 2020, that's why they put it here, the most recent version, 2020.3, 2021.1, 2021.2, whatever, all right? So, if you want to use the up-to-date version, that's not called Vivado directly. That's called Vetus or Vets. So inside it, you'll find Vivado. But if you don't believe in it, you can go in a Vivado archive and you download whatever you want. Now, when I used to use it until this semester, it was 2018.1. It's still valid, it's working, you know, it's perfectly fine. But if you like, you can download 21.2 substitute. I already downloaded last night. It's taken a huge amount of time to download it, by the way, and install it. Very, very expensive. Okay. Now, how if, let's say that, you know, you end up would like to go in 2021.2, right? In front of you here, there's a bunch of versions. Can you see it? Look at this. The unified version, 71.9 gigabytes. So you need to have enough space on your computer to install it. Okay? While you're installing, it will tell you, oh, do you want to install Vetus or Vivado or whatever? You can say just Vivado. Okay? Does it make any sense to everybody?
Yeah.
What is my honest advice to you? It depends on how your computer acts. If your computer is very strong, go with the highest. If your computer is like my computer, go with the lowest. Still the same. But maybe when you will be updating IPs, there will be like a little bit tricks I will tell you. Okay. Okay.
So all of these have what we need.
Huh?
Do all of these have what we need, or are there some specific
if you download this, you're fine. If you go ahead and just go in archive here and you go into like, you know, 2018, that will be straightforward, you know, 2018 one here for the one. Okay. Wait. So up to here, up to 20.2, 2020.2, there is Vivado. That's what you would find Vivado. But if you go into the level 2020.3, 2021.1, 2021.2, you will find Vetus. And inside Vetus, you'll find Vivado. Okay. Let me show you something in my computer that will make it better. So yesterday I installed Vetus 2021, right? Let me show you how I installed it and where, right? So here is my computer, share screen, desktop, yeah. So I went inside my PC, And here I put it in operating system, and then here's Linux, right? There is two different versions of the Vivado. There is one with license and one with what? Webpack. Webpack is the student version. So you download it, you don't need license. For me, I use license because I do some weird stuff. Okay. Anyway, have you noticed something? There is subfolder under Linux, right? Vivado, Vetus HLS, Model Composer, and DocNave and whatever, right? So the Vetus HLS, the one I was telling you using HLS, right? You remember when I was writing in front of you HLS? Vivado is the Vivado we are using. Personal problem with Vivado and Windows 10. Maybe you will not see it, okay? When you go into the icon and click on it, it doesn't work. It will just say timeout, timeout. Click again, timeout. Click again, timeout. And after 10 minutes, you will find whatever you clicked. Let's say you click 15 times, right? You will find 15 Vivado open. Then you have to close them one by one, right? I found something in internet helped me to solve this problem because it's a Java problem. I went inside here Vivado, and I go inside the 20.2, and I go inside bin, and then I search for what? Vivado.bat. I click on it, it opens. And if you look, it opens. See, this video will be actually loaded in the what? I will put it on the canvas before I leave the office tonight. Okay, so you guys can remember these notes. Okay, if it doesn't work, as I told you, you came into the icon in the desktop, you clicked, you keep clicking, and it gives you timeout, timeout. So it means that open later on will open many of them. So the solution, just go and run Vivado.bat. It will open. Make sense? Should I try in front of you? You can see it. Any questions so far? Oh. Any question? Any concern?
No questions, Professor.
I just want to be sure that you guys will not suffer. That's all I know. Okay. So you know exactly what you're gonna face, right? 2018.1 easy. 2018.2 easy. When you go up to 20.3, 2020.3, then you know tricks will happen. Okay. Now I will close this and I open it again in front of you. Better actually. So, as I told you, I go inside my Xyrex, but I have a problem with my operating system, I think, because I run weird stuff, in the top of this. You go here Vivado, you go here 20.2, you go bin, and then I stop in one of these like this highlighted, then I click V, then it go into the Vivado VAT, then I will just click on this one. Can you guys see the cmd.exe file? It's opening.
It just flashed, but it disappeared.
Yeah, it's Zoom. Hopefully you guys will back to school soon. It's gonna take some time. So let's talk until it's open, because it takes some time. It's really heavy stuff. Anyway, the question for you guys: are you gonna just go to the industry and tell them, by the way, I just work with Vivado? You need to know how to work with everything. That's my whole advice, of course. Like, it's FPGA end of the day. So the FPGA Intel has this FPGA, but it's using another software. It's called Quartus. It's using what? Quartus. Can you see the icon of Vivado is opening now? Hello?
Not yet.
It's opening now. Did you see it?
No, we can't see it.
Oh my gosh, I'm sorry. So maybe I can close like this and share again. What about now?
We see it now.
So if you see it, then you know, can you see the other one in the bottom? CMD
Yeah.
.exe. So what happened when I clicked on vivado.bat? The CMD.exe opened. Then it took some time to run some language called Perl, P-E-R-L. It's a language used to write the Vivado. It's called Perl and TCL, Tickle Script. Two guys are really important to be used for this high-end. SpaceX is using it. It's called PERL and TCL scripts. We're not gonna use it now, but I can show you some tricks with it later on, like an extra advantage thing that you know. Okay, now we open what? Vivado. Sounds good? To start a project with Vivado, what you're gonna do? You go into what? Create project. Create what? Project. Like, can you see what happened now? I got a new window say create a new Vivado project. Right? Can you see it?
Yeah, we can see it.
I said next. Then I will change the project location. So we can just put everything under the 5300, right? So they're gonna go in a PC. They're gonna go in the desktop. They're gonna go in the courses. They're gonna go in the 5300. They're gonna go in the Spring, and they're gonna go inside the Spring. And there I can make you a new folder. I call it what? Week 1 Spring, right? Let's say the project we need is what? And let's call it, right? Let's call it what? Test for fun, right? In X, next set. And then, you know, look, we came into the project type. We came into a project what type, right? So we have RTL project, we have post-synthesis project, and we have IO planning project, and we have imported project, and we have example project. Honestly, not everybody will tell you what is the difference, but I'm gonna tell you the difference, okay? Because you know, I believe that you know all of you guys are geek, so it's better for you to know everything. So RTL project is the one we're gonna choose, and the reason because we're gonna build our own custom IPs. We're gonna build our circuit based on the knowledge of learning the language. How can we run syntax for combinational circuit? How can we run syntax for the sequential circuit, and so on? So far, so good. What about those? What is those? Post synthesis. Imagine the following. Imagine that you know while we are running the tool. Do you remember I told you that you know you're gonna run synthesis and bliss and routes and routings and whatever until you map into the FPGA? You can actually shortcut one of the stages and you can put inside it files. So after synthesis, you don't need to re-synthesize again. No, you have file synthesis again. You put it inside the tool and continue. Is it going to be exist for this specific course? No. But you should know. Okay. IO planning project. So maybe you need to change the configuration of the input-output ports while it is running. Are we gonna use this in this course? No, but it is exist. Then imported project. Imagine that you know you already built a project a week ago, and you would like to use the whole entire project as IP for this week. Then why you need to rewrite it again? You take the whole entire project, you import it, and you put it inside the project. Are we gonna use it? We don't need it that much, but we can use it. Then example project is just making some templates so people can start using it if you are an instructor and you'd like to build some stuff with that. So now we understood which one we're gonna use. select what? RTL project. So far, so good. Any questions so far?
No, Professor, we're good.
Now, this files is telling you, do you have your own files that you're gonna invite it to be added to this project, or you're gonna create it? Since we started week 1, we don't have anything to import, right? So we're gonna create our file, right? When I click create, it's telling you what type of language you're gonna use. Is it Verilog or Verilog header? That means, including headers, or system Verilog or VHDL, or we're gonna build a memory file. Which one we gonna use? Verilog. So when I actually choose Verilog, the file that will be created will be .v. The file will be created will be .what? .v. If we're gonna choose VHDL, the file will be .vht. If we're gonna choose system Verilog, the file will be .sv. Okay? So here is Verilog, and the file name, I'm gonna call it what? Something. Let's call it what? Com PST test. And I say okay. So it created the file under the hierarchy of the project. So far, so good. Then next. Now is asking you, do you want any constraints? For your point of view, what constraints we are using? Somebody can tell. What is, can you forecast what constraints we have? Just like guessing. Somebody with something. I will tell you what constraint. XDC file. Do you remember? We are working with specific chip, with specific PCB board, right? So we have to have constraints for this specific board. Do you agree? So we need XDC file. If you haven't added, if you don't, just say create. And I would recommend to call it with the same name of the file to come. And next. Oh, what do you mean by constraint? Constraint that, the parameters or variables or, a set of environment that it needs to be set up on the project so it will be succeeded and to be deployed on the chip. So one of it is to know what is the input and output to the chip. You agree? IO. In that case, IO is the XDC file. XDC file. Okay, I will show it to you now. You have any other question, Mohammed? Anyway, now the type of the chip. What type of chip we're gonna be programming? What type of the chip we're gonna be programming? The board in my office, the one I have in camera, everybody can see me in the camera, right? I have something in my hand. This is the board. This board is the Nexus 4 DDR, the old version. So we need to know the chip name, that black box. I actually have my finger on it, on the board. So imagine this is the most important piece in the board. The rest are just like iron. So we're gonna search on internet now to find the name of the board. Everybody can see my web browser?
Yes.
Yes.
So now I'm gonna go in the web browser and imagine that I don't remember the name of the board, right? So Nexus 4 DDR, and I click like this. Then I need to search for the chip name on it, right? Here, this is the chip name. Can you see it? ECE3300 and -1 is the speed of the electrons, and CSG324C is the packaging. Do you know that when they build a chip, they make something is called die, which is a bunch of transistors on it, right? And then the ceramic, the black ceramic is called package. So the black thing that you have, like a plastic, this is called package. And the CSG324 is the name of the package. So I'll go back here to the chip and I search for what? XC7A100T, and then I don't write -1, I write CS, the package name, and -1 is the speed here. So I select it here. So something to share with you, and over and over and over. When I search it for the chip, it gives me here a statistic about what is on the chip. You guys agree? So for instance, this one, it has -2 speed, L, that's a version. This is -2, it's a version. This is -3, is a version. And each of those, it has number of resources on the chip that I'm gonna use to program, okay? In that case, look, the IO count, how many pins on the chip we have? 324 pins. Are all of them usable, accessible by you? Of course not. Some of them already handed by the PCB board, and some of them already handed to be connected to the switches and the Ethernet and whatever you have, right? Sounds good so far? Available IO, 210. That means, those are the official. The available I can use as a user, 210. The rest went into the level of the PCB. Then the switches used for building combinational circuit on the FPGA is called LUT. LUT. We're gonna talk about this the whole entire course. LUT, look up table. Look up table. And the number of resources from this lookup table on the chip, 63,400 lookup table. There is RAM, there is memory on the ASIC of the chip. That means it's hardened on the chip, hardened. It's not software. It's not like switches. And it's called block random access memory, like a RAM. 135 units of this. There is no ultra RAM. This is in the ultra scale and Kintex and Vertex version, not in Artex. DSPs hardened on the chip. We have 240 that can multiply and add and so on. And we can access them with Verilog. And I will show it to you like an extra bonus for this course. The transceivers, we don't have it. You know why? We don't have PCIe. How many of you guys heard about PCIe? It's a serial communication protocol have been built based on the parallel communication protocol called PCI. Yes. There is FPGA boards I have here in my office, each one worth $70,000. It has PCIe. All of this transceiver. We don't give that much away. It says we have one, but we don't have one. We have a virtual protocol of PCIe, but not the physical metal, the bare metal of the PCIe. What is MMCM? So the maximum frequency of the internal oscillator inside the chip is a 450 megahertz max. Or 100 megahertz max, I'm sorry. If you would like to speed it up, you will need a booster. And this booster, there is analog and a digital. There is one is called MMCM, which is an IP hardened on the chip, is analog IP. I will show to you later how can we request it, and we just have maximum 6. And we have another one is called PLL, phase lock loop shift IP. Then those are the requirements for keeping your chip safe from the voltage. And if you notice the voltage in the minima and the ref is less than 1, and when they build the chip, they build something is called LVLP, which is low voltage, low power. That means, you know, you can run it with like a battery, like 1.5 with a regulator to decrease the amount of voltage from 1.5 to be fraction of 1 volt. Of course, on the chip here, there is regulators and so on to help you to communicate with 3 and 5 volt and pass to the chip this amount of voltage, 0.95. And the rest of the IPs, maybe it will need 5 volt and 3 volt. So far, so good? Or do you have any question? Any question? No question. We're gonna say next. Done. So this is give you a summary about what we have done. So this project is using this specific part chip. We are using RTX 7 and we are using CES3300, and my speed is -1. And I say, there is initialization, so it will build the hierarchy. So the project is a hierarchy of files we're gonna build. Take some time. It's a very heavy platform, software platform. That's why I recommend you, if your computer will not handle 2021, you can go lower, you know? Anyway, hey, why it takes forever? It's running in the background. Have you noticed that VHDL? I didn't say that. I said Verilog. So I just went in setting. Look what I did. I went in setting, and I said here Verilog. And I just say okay. We have to wait for this initialization. It takes some time. So maybe we can switch to the tab so I can work a little bit with combinational circuit stuff. Then we can build a little bit like a test toy, and we'll be done for today. I don't want to tire you. Okay? Anyway. Leave it creating itself. It takes forever, and then we can just go in my Zoom here, and I will share with you something. my screen?
Yes.
Now, we said we're gonna use the knowledge we have from the 2300 to start describing circuits on the platform that I just prepared with you now, right? So one of the things we need to know from 2300 is gates. You guys remember gates, right? What gates we have? We have NOT
And
gate.
or
We have OR gate. What else?
AND gates,
AND gates.
NAND gates, NOR gates,
NOR gates, right? What else? XOR. Exclusive OR, right? And we have XNOR, right? This is the XOR and this is the XNOR. And or not and you guys remember those? Or should I give you like a quick update? Which way you guys prefer? Okay. Now, NOT gate, if you remember, everything based on the truth table, right? So NOT gate, if you have A, it will be A reverse, right? So the table will be what? 0, 1. Here it's gonna be 1, 0, right? Here, AND gate. AND gate, sorry, AND gate, number of inputs, fan in, fan out. Number of inputs, we have 2 or more. Output just 1, right? So imagine this is A and B, and the output is C. So the table will be what? A, B, and C. If I have 2 inputs, so that means how many states this table will be covering. If you guys remember, 2 power number of inputs. In this case, 1, 2. So it's going to be 2 power 2, equal 4. Right? So here, 1, 2, 3, 4. What is this 4 are? 0, 1, 0, 1, 0, 0, 1, 1. Both are 0. One of them is 1, one of them is 0. All of them are equal 1. You guys agree? The regular expression, not the regular expression, the Boolean algebra describing the relation between the inputs and output is equal to f as a function of x and y equal c. It's equal x ANDed with y. And we said the operator AND is doing what? If one of them, if both of them are exist, the output is exist. That means here is 1. But otherwise, there is no output. You guys remember that?
Yeah.
yes,
Then the OR is different. OR A and B and C. So the equation is the following. X ORed with Y. It does look like add, but it's not add, okay? That's operator of OR. And the operation say, I have a truth table of A and B, so that means 4 states will be covered, right? 0, 1, 0, 1, 0, 0, 1, 1, right? And here is the C. The fundamental of this Boolean algebra equation is telling you if one of them exists or both exist, the output is exist. Otherwise, nothing is exist. So let's see. Nothing exists, nothing exists. One of them exists, the output exists. One of them exists, the output exists. Both of them exist exactly. One is exist. Right? So we call those the basic gates because Based on those, I can use them to build a new gates, right? Combinational. What does it mean? So, you know, if I have AND followed by NOT gate, it's gonna give the same effect of what? Yeah. If I have OR followed by NOT gate, that's gonna give me what? OR. Right? So pretty much the outputs here C and here is AB. It's gonna be the inversion of what? The F. Right? So the table of it would be like this. AB 1, 2, 3, 4, 0, 1, 0, 1, 0, 0, 1, 1. Then you know C. So this is inverter, right? And we learned from the inverter everything would be flipped, right? So let's go here and invert, right? That was many zeros and 1. So the output would be what? 1 and 0. You agree? Right? Same thing for this gentleman. And if we go ahead like this, A, B, C, 1, 2, 3, 4, 1, 0, 1, 0, 0, 1, 1, right? So, or that was 0 and the rest 1. If you flip it, it will be what? No, I think I made a mistake. Right? You agree? No.
Yes, everything's good.
Anyway, now, what else? XOR, right? So XOR A, B, C. So that C as a function of A and B is equal A ANDed with the complement of B, or with A complement ANDed with B. So you are using here and, not, or, not, and. Right? And building is not really hard, right? So it's like basically what? Here is the A, and it was the not gate of E, and here is then right? Same thing for the XOR. So XNOR, I'm sorry. A, B, C. So F, A, and B is equivalent to A ANDed with B, or with A complement, B complement. Right? And before I leave the XOR, we can make the truth table, right? A, B, C. 1, 2, 3, 4, 5. If you guys remember, do you guys remember min term and max terms, right?
Yes.
M0, M1, M2, M3, right? 0, 1, 0, 0, 0, 1, 0, 1, 1, right? So this is what M1, this is what M2, this is 0 and 0, right? You agree? Same thing here. If this guy's telling you like that, that means, you know, A and B and C. 1, 2, 3, 4. 0, 1, 0, 1, 0, 0, 1, 1. M0, M1, M2, M3, right? So AB, that means, you know, this. A complement, B complement, that means this. The rest, right? So we
This-
can learn.
Is this XOR or XNOR?
This is XNOR. This is XOR. So you can actually learn that, you know, XOR is looking for the odd number of ones, right? So odd number 0 and 1 is just one odd, 1. 1 and 0, 1. When it came 1, 1 even, right? 0. And when it's 0, 0, that means we consider in theory that it's even, so that's why it's 0. There, the vice versa. We know that, you know, with 0, 0, that means, you know, even 1, so it's gonna be 1. When it's 1, 1, it's even, it's gonna be 1. Those are odd, that's 0. I'm not sure what's going on with my Vivado, but you know, it's still actually going into the initializing the project. So I don't know, it's like drunk or something. Okay. So far so good. Maybe I can close it and reopen it. Can be like a problem in the software. Anyway, leave it for now and we'll continue. Okay. So now we finish all the gates, right? Then everybody know that how can you convert from gate to the other, right? You agree? You remember that? Or should we review it? No. Can you guys hear me? No.
Yeah, we can hear you, Professor.
Should we review it or you know it?
Review.
So if you would like to move from AND from NAND to NOR, what are we gonna do?
Do I add a complement?
Huh? So AND is what? This is the NAND, right? And I want it to be NOR. How it can be NOR? Somebody can help me. Who would like to help me?
Would be A or B with a not bar on top.
I will tell you a trick. NOR is A B like this, right? You agree?
Yeah.
Which is good. I will show you what we're gonna do now. Okay, now, but this is like that. So in this case, what we can do, this can be De Morgan as you know, as Lawrence said. So gonna be A complement, B complement, right? You agree?
Yes.
Perfect. In that case, to make this like that, so we need what? Huh? Somebody tell me.
It's a law, but I forgot the name. It's a more. I want to say Moore's law, but I feel like I'm
No,
wrong.
no, it's not more. But you know,
No,
think.
no.
You know, we have
Morgan's?
fun now.
You had to complement the whole thing, right? Because then it becomes A complement plus B complement of that.
So we'll just add a not gate.
Let me think. We can reverse engineer this, right? You know what is easy, man? Come on. We can take this to be like this. All right. You agree?
Yes.
So this gonna be this part, gonna be this part. So that means, you know, we need to do what? I'll show you now. A gonna be A complement, right? B gonna be B complement, right? You agree?
Yeah.
Then, right? What do you think? Let's try it, right? A became A complement, B became B complement, right? Now they are a NAND gate, right? So it's gonna be A complement, B complement, complement, right? You agree?
Yes.
So this case will be what? Will be A, B, right? Then we take this to what? Correct? What do you think? Yes, sir. So this branch built OR. This built what? The NOR. This is more difficult, but you know, there's some other easy stuff, like, you know, build and using NAND. How are we gonna do it? So it's A, B, right? But this one is A, B, so they're gonna be A, B complement. That's nothing hard. So basically you're gonna go like this. It's gonna be NAND, A, B complement. Put another NAND, it's gonna be A, B. So this is the equivalency of what? Make sense? Yes. Okay. Now we can move to the combinational circuit. Unless you guys have a question with equivalency. Any questions so far? No. Okay, no question. Now, combinational circuit. So normally when we talk about combinational circuit, we're talking about what? About the circuit that has a relation between inputs and outputs without involving what? Timing, without involving what? Sequential circuit, which is involving what? Clock. But still, the circuit, it has its own response time. So what does response time mean? Response time means AND gate, for instance, right? Here's input, here's an output. To produce output from input, this specific block will have its own TR, response time. Why? Because this gate is not just like a gate, it's a transistor. It's a bunch of transistors inside. Do you know that? So the time to move all of the current and voltage inside will take time until you know to produce output. So that's called response time. Adding these pieces together into a circuit between input and output, we will be doing it now as example. We're gonna build what? 1 bit full earth. 1 bit. what is 1-bit full adder? If you guys remember. So full adder is considering there is a carry in and there is 2 operands, A and B, I, because slip a little bit. And there is a sum output and there is a carry out. On the other hand, there is something called half adder. If you guys also remember, right? So half adder is like this: A, I, B, I, S, I, and there is carry out, but there is no what carry in it. That makes sense? Okay. So to build such a kind of circuit, if you guys still remember, we have to use what? Truth table, right? So let's build the half adder first. Half adder, we have AI, BI as an input, and now we have a multi-output. So we have SI and we have carry out. 1, 2, 3, 4. Somebody will tell me why we have 4 states if you remember, because we already have what? 2 inputs. And 2 power number of inputs will be defining number of states, right? So here is 0, 1, 0, 1, 0, 0, 1, 1. Right? And mean terms is M1, 0, M1, M2, M. Now it's adder. So the operation is adding input to produce output. Do you agree? So 0 plus 0, 0, there is no carry out. 0 plus 1 is 1, there is no carry out. 1 plus 0 is 1, and there is no carry out. 1 plus 1 is what? 1 plus 1 is what? 0, but this time there's carry out. Right? Anyway. Let's see this event. Okay, anyway, now to build this circuit, we have to look into every single one, unless that we're gonna use a K-map or we're gonna use subtulates that for the optimization. But we don't need, I don't think we need any optimization, right? Because this look like what? XOR, right? And this is a traditional AND, right? So SI as a function of AI and BI is equivalent to AI ANDed with BI complement, or with AI complement with BI, while the C out as a function of AI and BI is equivalent to AI ANDed with BI. You guys agree? Now to build a circuit is basically using whatever we had, right? So here what? Here is AI ANDed with the inversion of the BI, and also different color, the AI that can be connected to the BI, and they're gonna be SI. Then C out is AI BI, so we're gonna have a different color here. Now there is something in the aspects we need to discuss. All right, which is what? Which is critical path timing here, right? Even though that we said it's a combinational circuit doesn't have a sequential element for generating clock, but in the top of that, you know, we are looking for what? Critical path. Our critical path in this case is what? The longest path between input and output. So there is one path between input and output here. There is another path between input and output here. There is also another input and output here. There is another path between input and output. And there is the last one, which is the right? So how many passes we have? Hello? Hello, can you hear me?
I think your internet's cutting out. I don't think
Yeah.
we can hear you that well.
Okay, how many passes we have now?
5.
How many paths? Can you see the lights in front of you, the different colors? How many we have? Can you hear me, or it's already cut now? Hello?
Yes, we hear you,
Uh,
We can
Professor.
hear you
We
now.
have 5.
1, 2, 3, 4, 5, right?
What about BI to SI?
Yeah, we have another 6 actually.
So
Here's
6, right?
Yeah, you're right.
Yeah.
See, it's tricky. Good. Now, so we have all of these passes. We need to do what? We need to start thinking about where is the critical path, which is the longest path. So critical path is the longest path between input and output. Normally, when we are in a race, right, the fastest is the winner. For us to make the circuit stable, the slowest is the winner. So if we look without even know the weight of everyone, right, you will find out the longest path is the one, this one. Why? Because this one, it has the T of the NOT gate plus the T of the AND gate plus the T of the OR gate, right? So imagine this one. Let's say that, you know, let's make a table and say, you know, the NOT gate is taken one T of time. The AND gate is taken, for instance, 2T of time. The OR gate is taken, let's say, 3T of time. Okay? So let's put it here, right? It's gonna be here 1, here is 2, here is 3, here is 1, here is 2, here is 3, and here is 2, right? So the longest is gonna be what? 1 plus 2 plus 3. So you're talking about 60. So this circuit has to be running 60 this amount of time, otherwise the circuit will not perform 1 bit half adder correct. Do you have any question? Hello? Can you guys hear me? Sometimes I feel you guys cannot hear me. Hello?
Yeah, we can hear you.
From time to time, just let me know that you're still there. I'm gonna make the full adder, and then we're gonna move back to Vivado so we can program. Okay? I have a question for you. If I would like to test the full adder to see the half adder, whether that is working or not, what should I do? Somebody can tell me what should I do? If you want to test your circuit to see whether that's working or not, what is your strategy? Huh? Any idea what should we do? Generate inputs, right? And try to see whether the output is correct or not. Do you agree?